Hi students, in this video we will be discussing more theorems on group, right? As we saw in the last video, also we discussed three theorems, okay, on groups, right? Among them, first was if G is a group, okay, then A belonging to G, there exists a R, okay, there exists a R such that A raised to power R is equal to E, right? This was the first theorem. Okay, alternatively we can say, okay, every element of a finite group has a order, right? Secondly, we saw if G is a finite group, then and A power M is equal to E, then order of A divides M, okay. In third theorem, we saw the order of A raised to power K is equal to order of A, which was M, and GCD of, okay, GCD of order of A and K, okay. These were the now continuing from this, we will be discussing some more theorems based on groups, right? So now introducing you to the fourth theorem. It says if G is a group, okay, let me write it. If G is a group, okay, you write let G be a group, okay, and A, B, X belongs to G, then prove that first order of A inverse is equal to order of A. Secondly, X inverse A into X power K is equal to X inverse A power K X, right? Third, order of A is equal to order of X inverse A X, okay. And fourth is order of A is equal to order of B time A, right? So one by one we are going to prove this, okay. So first result is we have to show that, okay, and this we shall prove that order of A is equal to order of A inverse, right? Yes. Okay, let order of A is equal to M and order of A inverse is equal to N. So how we are going to prove this? We are going to prove this by proving that M divides N and N divides M, okay. This imply N is equal to M, okay. So see here from this statement, since order of A is equal to M, we will be checking what is A raised to power N, okay. So this means if order of A is equal to M, this means A power M is equal to E, okay. If I multiply both the side with the inverse of A raised to power M, which is A raised to power minus M, one second, okay, Okay, fine. So multiplying it by a power minus m, which is the inverse of a raised to power m, we get identity element here, and here we are going to get minus m. Okay, now it can be rewritten as a inverse power m is equal to identity. Okay, but we know what is the order of n in last theorem, in second theorem, right? We saw if a power k or something else is equal to e, this implies order of a divides k. So see here, this implies order of a inverse divide m. Okay, we have written here order of a is n, so this implies n divides m. Okay, so secondly, you see what is order of a raised to power a inverse. Okay, order of a inverse is n, this implies power of this would be identity element, so we can write it as minus n is equal to e. Now again multiplying both the side by a raised to power n, we get this, and then this is identity and this would be a raised to power n. This implies a n is equal to e. This implies order of a divides n. Okay, and what is order of a? It is m, right? So therefore m divides n. So these two yields that n must be equal to m. Okay, this implies order of a inverse is equal to order of a. Okay, so this is the first part of the fourth theorem number 4. Okay, now second part is, it says x inverse, sorry, it is second part, x inverse a x raised to power k is equal to x inverse a k x. We have to prove this. Okay, we are going to prove this for all k belonging to integers, right? So we are going to prove this by principle of mathematical induction. Okay, so we shall prove this by principle of mathematical induction. So in that we do first, what we do first, we prove that result is true for n is equal to 1. Okay, for k is equal to 1, for k is equal to 1, what can we write? So for k is equal to 1, x inverse a x 1, it is equal to simply this thing only. Okay, which could be written as x inverse a power 1 x. Okay, so therefore result, above result is true for n is equal to 1. Now for assume that result is true for sorry, it was k is equal to 1. Okay, assume that result is true for k is equal to n. Okay, why we are taking k here, k is equal to n? Because generally we used to take, instead of k we used to take n, but here k has been already given in the theorem. Okay, and the given part, so we will have to change our terminology, right? So that's why we are using this. Instead of n we are writing, okay, k. So assume that result is true for n is equal to k is equal to m. You write k is equal to m. That is, if result is true for k is equal to m, then we can write x inverse a x raised to power m is equal to x inverse a raised to power m x, right? So now using this result, this is the key step. Using this result, we are going to prove that result is true for k is equal to m plus 1. So we are going to write it here. We shall prove that this is the procedure we used to follow for the principle of mathematical induction. We shall prove that result is true for k is equal to m plus 1, right? So now you see, x inverse a m plus 1 can be written as x inverse a x m into x inverse a x, right? So it is equal to, since it is equal to what, x inverse a m x, using this result, okay, into x inverse a x, okay. Now clubbing these two terms, what we get, identity into a, okay. So we can write x inverse a m into a x only, because two elements in the center, that is x into x inverse, is equal to identity, okay. Nextly, clubbing them, okay, we get x inverse a m plus 1 into x. Thus these two are equal. Hence, therefore by principle of mathematical induction, given result is true for all natural numbers, okay, that is for all k belonging to natural number, right? But we have to prove this result for integers, right? So what numbers has been left, okay, 0 and negative integers, okay. Now we are also going to prove this result for 0 and negative integers, okay. When k is equal to 0, what will happen, x inverse a x is equal to कितना हो जाएगा ये, it is normally it is equal to identity. Anything power 0 is equal to identity, and identity can be written as x inverse x, because x is the element of G, right? We have written this thing initially in the fourth theorem, right? That a, b and x belongs to G, okay. And x can be written as x is equal to ex, so we can write it as ex. E can be written as a power 0. So from here we have reached here. Therefore result is true for k is equal to 0. Now when k is negative, if k is negative, we can write k is equal to minus m, where m is positive, okay. So in this case, x minus x inverse a x, k would be equal to x inverse a x minus m, which is equal to x inverse a x inverse and m, okay. So it is equal to, now use the reversal law, okay. It would be written first with inverse sign, okay, then this with inverse sign, okay, then this with inverse, which is equal to x inverse is equal to x. So we can write, instead of this we can write x only, power m, okay. since this is positive number now, and we have already proved this theorem, this result for the positive numbers, so we can directly write it in this way. This is equal to x inverse a minus m k. Okay, so minus m is equal to k, a raised to power k is equal to, so this thing is equal to this thing. So thus we have proved this result for negative integers also. Thus a result is true for all k belonging to integers, right? So this was the second part. Now third part, prove that order of a is equal to order of x inverse a and x. Okay, so firstly let order of a is equal to m and order of x inverse a x is equal to n. Okay, so if this is the thing, then it implies order of a equal to m implies a raised to power m is equal to e, and this implies x minus 1 a x raised to power n is equal to how much? E. Let us try to see what would be a raised to power n. Okay, so see, this see, using the result 2 here, okay, we get x inverse a into x raised to power n can be written equal to x inverse a power n x, so it is equal to e, right? So now taking this to the another side, we get a n x is equal to, okay, or you just write, okay, not taking and all, because you will be getting confused with this, multiplying, pre-multiplying and post multiplying with x. क्या किया यहाँ पे, पहले x से मल्टीप्लाई किया, ठीक है, और लास्ट में किससे मल्टीप्लाई किया, x इनवर्स से, और यहाँ पे भी क्या करोगे, पहले x से मल्टीप्लाई करोगे फिर लास्ट में x इनवर्स से. इट इज कॉल्ड प्री मल्टीप्लिकेशन एंड पोस्ट मल्टीप्लिकेशन. ओके, because group is not all the groups are not abelian, so we will have to follow this procedure, right? So this is equal to identity and this is also equal to identity. Identity into anything is equal to same again, so it is a inverse. Okay, so this is also, this is x into x inverse which is equal to e. So therefore we we have reached to the result that a raised to power n is equal to identity element. But we know order of a is equal to how much? Order of a is equal to m. So therefore order of a divides n, which is m. Okay, so m divides n. So here now you can see here, what is power of x minus 1 a into x? What is power of the, what is the power of this element? If power of this element is equal to m, what is the result? Okay, so it could be written again in same way. It is equal to x inverse a power m x, so it is equal to e, so x inverse e x, which is equal to x inverse x, which is equal to e. Therefore this power is identity. Okay, but order of this is n, so therefore n divides m. Okay, so now both these implies that n is equal to m. Thus we can say order of a is equal to order of x inverse a into x. Now in fourth part we have to show that order of AB is equal to order of BA. You do but in this replace A by AB and X by A. Okay, we get order of AB is equal to order of, in place of X you are going to write A. Okay, A inverse, and in place of A, AB. Okay, in place of A, X, you are going to write A. So this is identity. So we are left with order of BA is equal to, sorry, order of AB is equal to order of BA. Okay, so this was the fourth result. Okay, thus hence the result. Okay, so this was the fourth theorem. Now we are going to prove fifth and last theorem. Okay, okay, so a statement of this theorem is, if A comma B be any two elements of a group G such that AB is equal to BA and GCD of order of A comma order of B is equal to 1, then prove that order of AB is equal to order of A into order of B. Okay, so we are going to prove that order of A, B is equal to order of A into order of B. Okay, proof. Let G be a group and A comma B belongs to G. Let order of A is equal to M and order of B is equal to N and order of AB is equal to K. Okay, then we shall show that क्या शो करना है हमें कि order of AB is equal to order of A into order of B. So this is equal to K, this is equal to M. So we shall show that K is equal to M into N. So how we are going to show this? We are going to prove that Mn divides K and K divides Mn. Okay, so firstly you see, okay, A B raised to power nk, ये किसके इक्वल हो जाएगा? We can write it as A raised to power nk because it is abelian. Okay, not abelian because AB is equal to BA, so therefore it is equal to A raised to power nk, B raised to power nk. Okay, you see order of A is equal to order of B कितना है? n है, तो इसका मतलब क्या हुआ? B power n is equal to E. This implies अगर bn का कुछ भी पावर कर लें k like, so it would be again equal to E. Okay, so this implies A power B power nk is equal to identity element, so it is equal to A nk into identity element, which is equal to A raised to power nk, right? Also you see AB का order क्या है? K, so therefore AB raised to power k is equal to E. If I raise its power, अगर फिर से इसका कुछ power ले लूँ, like if I take its power n, okay, then it is equal to E raised to power n is equal to E again, so therefore we can write it is equal to nk is equal to E. Okay, so it is equal to E, right? This is equal to E. And C first and last. So this implies E raised to power, E is equal to, identity is equal to A raised to power n k, which implies A n k is equal to E. This implies, देखो ऑर्डर कितना है ए का, m है ना, तो therefore m divides n k. One more thing you need to see here. We are given that order of a comma order of b is equal to k, right? It is equal to m and it is equal to n. So GCD, okay, it was GCD, I'm sorry, I said something wrong, right? So GCD of order of a into comma order of b was equal to 1. Order of a is equal to m, order of b is equal to n. So therefore GCD of m and n is equal to n. What does this it imply? It implies m does not divide n and n does not divide m, and n does not divide m. So here, see here, m does not divide n. This implies m divides k. Okay. Similarly, you will come to know that E is equal to a b raised to power mk, which would be equal to b raised to power mk. Okay. So this implies n divides k. Okay. Or you just write simply similarly n divides k. Okay. Now we have a property in number theory, right? If m divides k, n divides k, then LCM of m and n also divides k, and LCM is denoted by these brackets, okay, square brackets. So this implies LCM m comma n divides k. Okay. One more property is there. LCM of m and n when multiplied with GCD of m and n is equal to multiplication of m and n. We know here, okay, so we can write it here, since okay m into n and GCD of mn is equal to mn. Okay, we know this is equal to 1, right? So this implies mn is equal to LCM of m and n is equal to m into n, right? So we can replace this by mn. So mn divides k. So this is the first. Now secondly, okay, remember this equation 1. Now secondly, we are going to prove now k divides mn. Okay, this part is for this thing. Okay, secondly, order of AB is equal to k. Okay, right? But what is if I raise power of AB की पावर अगर mn कर दें तो ये कितना हो जाएगा, amn bmn. अब देखो ए का ऑर्डर क्या है, m है, सो देयरफॉर a पावर m इज इक्वल टू आइडेंटिटी. अब फिर से इसका कुछ पावर कर लूँ, वो भी कितना रहेगा, आइडेंटिटी. सो इट इज इक्वल टू आइडेंटिटी. सिमिलरली इसका पावर b का ऑर्डर क्या है, n है. अगर इसका b ऑर्डर ऑफ b इज इक्वल टू n, order of b is equal to n, therefore b power n is equal to identity element. If I raise its power again, then it would be okay. If I write b, I mean to say b power mn would be also again equal to identity element. So identity into identity is equal to identity. So therefore ab power mn is equal to identity, right? This implies order of AB divides mn, but order of AB is k, so k divides mn. So from 1 and 2, okay, So 1 gives mn divides k, and 2 gives k divides mn. Therefore from 1 and 2, k is equal to m into n. K was what? Order of AB, and it was order of A, and n was order of B. Hence the theorem. So this was all about the theorems based on groups. Okay, and this is it. This was it which I wanted to tell you about the theorems. Okay, these were the results on groups, right? So in next video we will be discussing some examples, okay, on these theorems, and also on the definition of groups, right? Okay, so thank you.